Hello and welcome to Lesson 4.5 over congruent triangles, specifically ASA, AAS, and HL. We're going to talk about angle-side angle theorem, angle-angle side theorem, and what we call the hypotenuse leg theorem for proving triangles are congruent in this lesson. Previously, we used side-side-side and side-angle-side postulates to prove that triangles were congruent. Now we're going to learn about three more: angle-side angle, angle-angle side, and hypotenuse leg. First off, I want us to talk about what the included side actually means. We talked about included angles in the last lesson, so the included side then is kind of the same deal, but a side between two angles. Okay, the side located between two consecutive angles of a polygon is called the included side. And so what we have here is that if two angles of one triangle are congruent to two angles of another, and the included sides are congruent, meaning the side shared by both angles in this triangle is congruent to the sides shared by both angles in this triangle, then the triangles have to be congruent, angle, side, angle. So what we want to look at here in example 1 is figure out if angle, side, angle can actually be used. So let's look. In triangle NKL and triangle LMN, here's what we know. We have parallel sides KL and NM. That means that we have angles here and here that are congruent because they're alternate interior angles if LN is your transversal. And we also know that side LN is congruent to itself, but we really don't have any other information. So what we've covered here are angles that are congruent and a pair of sides that are congruent, but that isn't enough. I need another angle. I would need to know that angle KNL is congruent to angle MLN, but I don't know that. If I knew these sides were parallel, I could say that, but we just don't have enough information. So our answer is no. We would need to know that angle KNL is congruent to angle MLN. Then we could use angle, side, angle. All right, let's take a look at part B. On part B, we are given two triangles, kind of like that hang glider example from the previous lesson. Want to determine if we can use angle, side, angle. Well, here's what we have. We have two angles here that are congruent. We do not know that the included sides are congruent. We're not marked that way. They don't tell us enough information. We do know that there are a pair of sides congruent, these sides here that are shared, but that is not the included side between those two. So here's what we would need. Again, we cannot use angle, side, angle. We need the included sides to be congruent. All right? But what you notice about part B is that we have angles and a non-included side that are congruent. Now, what we could say to eventually use angle, side, angle is that since these two angles are congruent to these two, the third pair of angles are congruent. So then we could use angle, side, angle because these angles and these angles are congruent, and this makes that the included side. But we can't directly say angle, side, angle. Now, in your notes, we do have the angle, side theorem also. Since we, like I talked about in this previous example, that if we use the third angles theorem, we would be able to use angle, side, angle. It's really easy for us to then just make this angle, side. So if any two angles of one triangle are congruent and any one side are congruent to the other one side, we really can prove triangles are congruent. It's either angle, side or angle, side, angle. You just have to figure out which one you should use. All right, before we go any further with the next example, there is one other theorem that we want to use, and this lesson kind of leaves it out and brings it back in later as an extension when you're looking at your textbook. But you'll notice we've talked about side, 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 and side, angle, side in lesson 4.4. And then we talked about, in this lesson so far, angle, side, angle, or angle, side. But we also have one other option. Now, I've mentioned before that we really don't have side-side angle, which if you flip that around backwards, you'll get a word that we're not supposed to write or say. It's not very nice or polite. But we do have that scenario when we're dealing with right triangles only. And in right triangles, you have parts of the triangle called the legs and the hypotenuse. And if we have a right triangle, and only in a right triangle, we can say if the hypotenuse and leg of one triangle are congruent to the hypotenuse and corresponding leg of another right triangle, then the triangles are congruent. We call that HL, or hypotenuse leg congruence. But they have to be right triangles, otherwise you don't have sides that can be called hypotenuse and leg. Okay, so we will use that in this lesson also. So let's go ahead and look at the next example. Now, I've already marked some things out here for you. In this triangle, we're trying to prove, or in these triangles, we're trying to prove triangle ACD is congruent to ECB. And I've drawn them out for you separately here since they overlap. Now look at what you're given. We're given that angle DAC and angle BEC are congruent. Basically, angle A is congruent to angle E. Since we already know that, I don't have to write it out the long way. We can just say angle A is congruent to angle E, since there's only one angle at each. We also know that DC is congruent to BC, so there's a pair of congruent sides. But notice both triangles share angle C, which is congruent to itself. So what we have here are two angles of one triangle congruent to two angles of another, and a non-included side congruent. So I don't want to use angle side angle because the angle is, or the side is not included by the two angles. I want to use angle angle side. Those kind of go in opposite order. Angle angle then side. All right. So we're going to use angle angle side to show these triangles are congruent. So we're going to start off with the given information. Angle DAC is congruent to angle BEC because it's given. And then before I state the other given, I'm going to do this in a little bit different order. I am going to go ahead and say angle C is congruent to angle C by the reflexive property, because I want to kind of do these in order. I want to do the pair of angles first, the pair of angles second, and then the non-included side, which is given to you. DC is congruent to BC because it's given. Well, then the triangles are congruent by angle, angle, side. So we can say triangle ACD is congruent to triangle ECB by angle, angle, side. All right, so pretty straightforward. You just have to figure out, are the congruent sides the included sides between the two pairs of congruent angles? All right, for this next proof, you'll notice that in our plan, there are two possible approaches we can use. And I'm actually just going to pick one of them for this example. And if you need some extra room, feel free to get out a blank sheet of notebook paper to copy this down. But you should have enough room in your notes to do this. Okay, we're going to pick the first possible plan. Okay. And it tells us to use parallel lines. One of those theorems like alternate interior angles, alternate exterior angles, something like that, and a vertical angles to prove angle angle side, instead of using a parallel lines theorem twice. Okay, and so we're going to do that, and so we're going to look at what we're given and try and figure out what we can say from that. All right, so here's what we're given. We are given that RQ is congruent to ST. We have congruent angles here and here, and that creates transversals, either RT or SQ, whichever one we decide we want to use. And then we're also told that they are parallel, and that's going to make these alternate interior angles congruent. So that's what we're going to do. And then we're going to use vertical angles here, RUQ and SUT. And then we are going to be able to talk about angle angle side. And so I'm going to do this proof the way I showed you to do this in class. Okay, we are going to set up angle angle side and do a flowchart proof. Angle angle and side. We're going to take the given information and see how we can build a pathway to eventually use angle angle side to show that the two triangles, one on the left, one on the right, are congruent. So let's start with the first given, that RQ is congruent to ST. Those are sides, and so in fact that given is all the way here to the right, that segment RQ is congruent to segment ST, and that is given to us. So there's one pair of congruent sides, and these are going to be the non-included sides between the angles I use. So I'm going to use two angles congruent to each other, and then the vertical angles we'll talk about so that we are not using the included side. All right, so I'm going to go back here and use the other given statement to set up my first pair of congruent angles, and that is that RQ is parallel to ST. And that is given to me. All right, and so since they're parallel, I'm just going to pick an angle along a transversal. So let's say I pick angle R. That would be an alternate interior angle with this angle T. And since these are parallel lines and RT is your transversal, these alternate interior angles are congruent. So this parallel line statement leads me to the fact that angle R is congruent to angle T. I could have used Q and S, but I just chose R and T by the alternate interior angles theorem. Okay? There's a pair of congruent angles. I need another pair of congruent angles. Well, we already kind of planned out that we're going to use our vertical angles here. The vertical angles would be RUQ and then TUS. So I can say angle RUQ is congruent to angle TUS because they're vertical angles. So the reason is the vertical angles theorem. And there's another pair of congruent angles. So I've shown two pairs of congruent angles and a pair of congruent sides, that's the non-included sides. So I can use angle, angle, side to show that the triangles are congruent. So I'm just going to make arrows to say that triangle RUQ is congruent to triangle TUS by angle, angle, side. And that's how we can do that proof. So let's talk about which method out of all four that we've talked about so far we would use to prove triangles are congruent here. So let's look at the given information. This goes back to an example we've already done. We have angles that are congruent here, angles that are congruent here, and the shared sides that are congruent. So there's angle, angle, and then the shared side being congruent to itself by the reflexive property, side. So this would require the use of angle, angle, side. Okay. Then let's take a look at part B. We've got two triangles here. We have congruent sides here and here. We have parallel sides. Now parallel sides tell us the alternate interior angles are congruent. Okay, we have the correct markings there. So there's a pair of angles. There's a pair of sides. But then the shared side BD is congruent to itself by the reflexive property. So there's a pair of sides. Now notice that the included angles are between the sides that are congruent. So we can use side, angle, side. All right, lastly, let's take a look here. We want to look at the given information. We want to mark that on the diagram if it's not already given to us. Here we are told that JL, this middle line, bisects angle KLM. Well, that alone would tell us that these are congruent angles. We are given that these are congruent angles, so we have angle, angle, and then JL is congruent to itself by the reflexive property. So again, we can use angle, angle, side, since the sides that are congruent are not the included sides. So here's a just quick summary of the different kinds of ways to show triangles are congruent